There we go. I will begin with a word of prayer. So here we go. Dear Father, we thank you for this day and for this wonderful weather. Help us to enjoy it and to learn more about your creation today, Lord. In your name I pray. Amen. So as you guys are well aware, we are in Introduction to Topology. By Gamelin and Green, I am currently working on butchering his proofs on compactness today. So we'll see what we can do. This is section 5. And so he has a couple of introductory paragraphs here about compactness. And I think my brother would be particularly happy because my brother will come to this conclusion in the last year or two. And it's simply this, is that compactness is finiteness. Right? So the concept of something being, if it's compact, it's in some sense finite. Right? And it's not literal, but that's kind of an analogy to be had there. And he basically says that here. He says there is a certain class of properties that finite sets have trivially that are retained by compact sets. For instance, it will be seen that every continuous real-valued function on a compact space is bounded and assumes its maximum and minimum values. Like he says, these claims are trivially true for finite sets, but they're also true for compact sets. So compactness is in some sense a kind of finiteness. Now, but he gives us so this section, again, is in the context of metric spaces. The ultimate result of this section is, I think, his theorem, I think it's 5.1. The special case of that is the Heine-Borel theorem, which you might have studied in the 431 course here. All right. So we're gonna be exploring those ideas today and hopefully proving some of them. So let's start with the definition. And this is section 5, compactness. And so first of all, definition, a family of sets U alpha, all right? And alpha here is taken from some index set lambda, is said to cover S if S is contained in the union of this family. An open cover of a metric space, all right? What's an open cover of a metric space? Open cover of metric space X has, the union over the open cover equal to the metric space, right? And what else? What makes it an open cover? What's that? Right, each U alpha is open in X, right? Remember, to say a metric space means we have a distance function, so we're talking open in the metric sense, right? Each point's interior, there exists an open ball of some radius around each point, right? So that's an open cover in a metric space. Now here, finally, so cover, open cover, and finally compact. Metric space X is compact if every open cover U alpha has a finite subcover. More specifically, so that is there exists, let's say, u1, u2, dot un, such that x is equal to u1 union u2 union un. So this would be a compact metric space. Now, every open cover, right? Every open cover has to have a finite subcover. So what's not compact? Let's get that out of our system right away. How about Rn? Right? What if we look at Rn and we use, I don't know, how about like, yeah, something, right, let's let u be something, oh, what would you say? Oh, so like un is equal to b of 0n, like the ball of radius n centered at 0, n equals to 1, 2, 3, 4, dot, 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 dot. Right? There's no finite subcover of that which covers all of Rn, right? I mean, you pick a finite subcover, right? Then there's a largest n in that finite subcover. I pick a point, distance n plus 1. Game over. It's the same stupid argument that, you know, natural numbers are not finite. Like, you can always go beyond wherever you got to, right? We played this childhood game. I can count higher than you can. No, you can't. Give me your biggest number. Fine. And then, well, you're a kid. You usually do something like square it, right? You don't just add 1. That's not dramatic enough. You're like, my biggest number is infinity, and you'd be like, I am infinity squared. Nobody do this when you're little? No? You did this. Right, yes, okay. If you say infinity, they call you a cheater. But yes, so like Rn or R, these are not going to be compact, all right? Furthermore, another definition, I guess I can put it up here. Metric space X is totally bounded. Totally bounded if for each epsilon greater than 0, there exists a finite number of open balls of radius epsilon which cover X. All right? Maybe it's good for us to look at an example of a compact metric space before we go on, right? For example, the unit square. We just look at the unit square. So this would be what? 0, 1 squared, if you like, right? So we're looking at, you know, this contains x and y such that what? Now, maybe it's not immediately obvious that you take any possible open cover of this space, right? A set of open sets whose union forms the whole thing, right? And I guess the question is, what metric am I using, right? Let's say Euclidean metric, all right? I do literally mean open disks. But I'm telling you, I'm claiming that if you took any set of open disks which cover this square, you could pick a finite number of those and cover the whole thing. You can kind of see it, maybe, but that's not a proof, of course. Is it totally bounded? For each epsilon, that I can actually prove. You give me an epsilon, right? Like, how about epsilon equals to 2? I'm cheating. So, like, epsilon equals to 2. Pick the center point, and I think that gets pretty... Well, even square root of 2 would do it, right? A little bit more than square root of 2, but certainly 2. This, the open disk with radius 2 covers the whole thing. So if I like epsilon equal to 2, then one disk covers the whole thing, right? If we looked at, like, I don't know, radius 1/4, right? You could do something like, I mean, I don't know. I could do this, I could do that, I could do that, I could do that, and I just need, I need another one here, and I need another one there, 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 up to the limits of my artistry. I mean, sure, it could be a pain to actually get enough to cover it if you pick a small enough radius, but it's clear that there's a finite number of disks which are going to cover it for a given radius, right? You can think of it in terms of like flooring, right? If you're somehow using like circular tiles that overlap, but not completely, eventually you're going to use up all the area in the unit square, right? I don't know. Let's find out. What is the interplay between these ideas? That is the question. And that is answered by the following theorem, which I think would take us the better part of, I don't know, probably 3 hours to completely prove. Theorem 5.1. I mean, I'm going to try to prove a fair amount of it today, but we'll see what we get done. The following are equivalent for metric space X. 5.1 is X is compact, which here means what? Every open cover permits a finite subcover. You may have been taught a different definition of compact in reals. Oh, that was your, okay, good. Some people use a sequential definition of compactness in reals. The original, every... Oh, that, so you did take a topological definition, even in reals. Very good. Some people use 5.2 as the definition, though, in reals. 5.2 here is every sequence in X has a convergent subsequence. All right. And then here is the one you were kind of getting at, Jonathan. X is totally bounded and complete. Aha! Totally bounded and complete. What did complete mean? Right, Cauchy implies convergent for a sequence. The other direction is free. Every convergent sequence is Cauchy. But in a complete metric space, Cauchy implies converges. So the following are equivalent. In the case that X is equal to the real line, or sometimes Rn, this becomes the Heine-Borel theorem. So Now what he says the proof of theorem 5.1 will take most of this section. For now, we content ourselves with proving the straightforward implications. Just 5.1 implies 5.2 implies 5.3. Let's take a swing at one of those to wet our whistle, yeah? So I'll work on 5.1, implies 5.2. What do we start with? He says, suppose X is compact. That seems like, I mean, I haven't lost him so far, right? If we're proving a direct implication, I think assuming 5.1 seems like right? We can all agree this is the right first move. All right, next he says, let y sub j equals 1 to infinity be a sequence in X. All right, what do we need to show then? Right. He says, suppose that for each x in X, there exists epsilon equal to epsilon of X positive, such that only finitely many terms of the sequence lie in what? For each x in X, there exists epsilon of X positive, such that only finitely many terms of the sequence y sub j lie in that ball. For each x in X, there exists epsilon equal to epsilon of X positive, such that only finitely many terms in y1, y2, da-da-da-da, right, lie in B of X comma epsilon of X. Well, this feels like the start of a contradiction, because that's clearly not so cuckoo. Because if I just take the constant sequence, you know, why not, 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 I mean, why not? Then pick any ball of radius epsilon centered at y naught, then the whole stupid sequence is in that. So I think you're right. This is the start of a negation. Which, if we read the rest of the paragraph, we'd come to learn that. But this is a proof by contradiction for sure. Yeah. So we're assuming that for an arbitrary x, there exists an epsilon such that only finitely many terms are in the open ball. We're hoping this leads to an absurdity. If this is absurd, then what does it give us? It gives us that there exists an x such that there are infinitely many terms in some open ball around that point. Yeah. For each radius also, yes. Okay, so let's get to it. He says well then the set of open balls B, somehow we got to use compactness, right? So he says the set of open balls like this, what's that? Yeah, open cover of X, right? Which implies by compactness what? Yeah, there's got to be a finite subcover. There exists, let's say x1 through xm, such that what? Such that x is equal to b of x1 epsilon 1, find semicolon. I'm already dropping my semicolon. Union b of x2 epsilon 2 union da-da-da union. And then what good does that do me? he says, since yj belongs to b of x of I, epsilon x of I, for only finitely many indices j, we may conclude that there is a grand total of only finitely many positive integers, which is nuts. This contradiction shows that there exists an x in X such that each ball of radius epsilon contains infinitely many terms of the sequence y sub j. Do you guys get that? So what's he doing here? Right. So if we have, okay, so we have finitely many terms of the sequence in each one of these balls, right? Which means that there are what? A finite number of terms in the sequence in all of X. Yet Y is an infinite sequence, which means it doesn't have finitely many terms, it has infinitely many terms. That's the contradiction. So if there actually existed this open cover, each one of these only containing finitely many things in the sequence, that means that there's a total of finitely many terms in the sequence, which implies that the natural numbers are finite, which of course is not true. Okay. All right, so then we use this data to create a subsequence. So he says, okay, now construct a subsequence of y sub j as follows. He says, choose j1 such that what? Such that y sub j1 is an element of b of x radius 1. So we're picking the x for which there exists infinitely many terms in the sequence, all right? Picking the x which exists because of the contradiction, all right? He says, okay, that's j1. And then he says, since yj is an element, yj1, I lost my place already, curses. Since yj1 is an element of b of x1, a ball of radius 1 centered at x, what's that tell us? That tells us that, and y sub j is an element of b of x 1/2. By assumption, x is a point where any epsilon around x has infinitely many terms in the sequence, right? It's a place where the sequence is accumulating. So if I look at radius 1/2 around x, there's infinitely many terms in the sequence. There's infinitely many y sub j that are within 1/2, right? And what's he do? He says, okay, so pick y sub j2, pick j, so let j2 be greater than j1 such that what? Y sub j2 is in the ball of goodness gracious, 1/2. All right. And he says, generally speaking, pick y sub jn such that it's in the ball of radius 1/n. So to draw a picture of what's going on here, we have x in the center, right? So I just did, 1, 1/2, 1/3. And the point is you're selecting a y sub j1, which is in the outer rim. You're selecting y sub j2 in the middle, y sub j3 in the interior, and you just keep picking one, from each as you zoom in further and further and further, every time you pick a y sub j that's in between these bands. And you can do that because there's infinitely many of them. All right, anyway, so the larger point here then is that, so you have this sequence, right? Y sub j k, k equals 1 to infinity, where the distance from y sub j k to x is what? It's less than the distance from what? Yeah, let me just, I'm sorry, it's 1 over n, right? Oh, yeah, I'm sorry, 1 over k, yeah. So the first one is within 1 unit of the center, the second one's within 1/2, then the third one in this subsequence is 1/3 from the x. All right, so what happens as k goes to infinity here? It goes to 0, which is to say that this subsequence converges to x. And there you go, that's 5.2. Every sequence in x has a convergent subsequence. What's that? It took what? Yeah. Well, I'm sure the proof that you gave in real analysis was a little bit more careful than what I just did. Not? Ah. Yeah, I see. All right, so then, let's see here. How about 5.2 implies 5.3? Let's see if I can sketch some of that. He says, suppose 5.2 is valid. Let x sub j be a Cauchy sequence in x. By 5.2, x sub j has a convergent subsequence. And by lemma 2.2, the sequence x sub j itself converges, hence x is complete. Let's see here, let's try to run through that right quick. So he says, let x sub j be Cauchy sequence in x, all right? He says by assumption, right? There exists a what? A convergent subsequence of this, right? And then he says, by lemma 2.2, the sequence x sub j itself converges. What is lemma? Indeed. So lemma 2.2 is back on page 9, and the lemma was this. If x sub n is a Cauchy sequence, and there is a subsequence which converges to x, then x, the whole sequence converges to x. That's right. So it might be worth going through the proof of that. I don't think I did last time. So let's actually prove lemma 2.2. Lemma 2.2 says if we have x sub n Cauchy, and there exists, let's say, x sub n k, which converges to x, then x sub n converges to x. So here's the proof of that lemma 2.2. Let's go through it. So the proof, he says let epsilon be greater than 0. All right, and we're going to assume, of course, that we have what we have a Cauchy sequence and a convergent subsequence, right? He's like, choose k greater than 0 large enough so that what? The distance from xn to xm is less than epsilon over 2 whenever n and m are greater than k, I would suppose. Fine, greater than or equal to, there. And he says also, choose L greater than 0 such that the distance from x sub n j to x is less than epsilon over 2 whenever n sub j is greater than L, I would suppose. Oh, actually, whenever, not n sub j, but j greater than L. So before I go any further, do you understand why we can do both of those things? Does that make sense? The one is because the original sequence is Cauchy. The other is because the subsequence is convergent, right? So we can go far enough out in the subsequence to get close as we like to the limiting, to make the distance to the limit point x get as small as we want. And then what do you think he's going to do? He's going to say, okay, so let n, big N, be the max of what? How about little m, little n, and L, right? Did I do? Oh man, k and, oh, you're right. It's max of k. Good grief, sadness. Yeah, I'm an idiot. Those are indices. What am I doing? So the max of k and not L, but actually n sub L. All right. So he says if m is greater than or equal to n and n sub j is greater than or equal to n, then check it out. The distance from xm to x is less than or equal to triangle inequality. Distance from xm to xn sub. Oh, this is messing with me. Oh, words. X sub n and then comma x sub n sub m. Say that 5 times fast. And then plus the distance from x sub n sub j to x. What? That feels like a typo. I think they're either supposed to both be, I think this is supposed to be a j here, right? Then what? Well, then that's less than, so we're far enough out that that's less than epsilon over 2, and we're far enough out that that's less than epsilon over 2 using both of the which then shows you that, hey, we can make the distance from the mth term in the sequence to x as small as epsilon, epsilon being arbitrary. This shows that the sequence x sub n tends to x as m goes to infinity, which is the content of lemma 2.2, that Cauchy, and a Cauchy sequence with a convergent subsequence is necessarily convergent to the same limit as the Cauchy subsequence. Okay, so getting back to 5.2 implies 5.3, what do we know? We have a Cauchy sequence with a convergent subsequence So that means that the sequence converges to X, right? So what does that say? Oh, that says that Cauchy implies convergent, doesn't it? So put this all together, we have that X is complete. Right. So the assumption of 5.2 paired with lemma 2.2 gives us the completeness of the metric space. So what's left to prove? Right, so it still remains to show that it's totally bounded. Lost my place. Don't worry, I'll find it again. All right, so he says, again, assume 5.2 is valid, let epsilon be greater than 0. We wish to cover X by a finite number of open balls of radius epsilon. Uh-oh. So we're almost done with real analysis. We're working on it. I'm going to erase the definitions from the start of today before Sam has a chance to qualify them. Okay, I'll behave. I'll work over. Can I work over here? I think so. All right. I haven't erased yet, Sam, so it gives you a sense of where we are. Now, so he says, suppose 5.2 true. Let epsilon be greater than 0. As he says, we wish to cover X by a finite number of open balls of radius epsilon. He says, let y1 be an element of X, some arbitrary point, right? He says, if the ball centered at y1 of radius epsilon is equal to X, right? Oh, he doesn't say that. He says, suppose it's not equal to X. I guess if, well, you know, what if it's equal to X? Then what? Then I guess we've just shown it's totally bounded, right? Because one ball. Like my initial stupid radius 2 ball around the unit square. But if it's not equal to the whole space, then what does that mean? What's that? Yeah, we can draw. I mean, here's a picture. Pictures are dangerous, of course, but here's the ball radius epsilon. Well, there has to be a y2, which is in X with the ball removed, right? There has to be a point out there somewhere. Where was I? So he says, let y2 be any point in X with the ball of radius epsilon centered at y1 removed. All right? Then what? Oh, by the way, if, let's see here. Well, I'm sorry, I lost my place, guys. Just a second here. Then what? What does he do with that? Oh, right. Yeah, I was thinking the next thing, he should also think about. Right. Right. So if this is a picture of the epsilon is fixed, right? It's the same radius that we're using. Right? They're kind of like all. So in this context, if my metric space happened to be this slightly crooked rectangle, we'd be done. Right? If the metric space actually was this, then that would suffice to show it's totally bounded. Right? But anyway, we can continue in this fashion, right? If so I guess the thing is if the union of the ball around y1 and the ball around y2 is not the whole space, then there must be what? There must be y3, which is an element of x with the union I equals 1 to 2 of the ball of these, right? Like remove those balls, there has to be a y3 in that complement, right? What does this do for us?
You can keep constructing them, and then you make a sequence of those y's. And if there's only a finite number of y's, then we show that it's totally bounded. And if there's an infinite number of y's, now we have a sequence that will have to have a conversion subsequence.
Let us put that on the board. So what did you say again?
We can keep constructing y's, and then he gets to like a yn plus 1, and then plus 1.
And yn plus 1, and then what?
And if we ever get to the point where we've covered the whole metric space, then we show that it's totally bounded.
If we cover all of x, then can show, then we have shown x is totally bounded.
And so then, I don't know exactly what he does, but I'm assuming that he says, then we can assume that there's an infinite number of y's.
So there's two cases. Either this algorithm truncates. If it terminates, like my stupid picture, it terminates at 2. We've covered the whole space, right? Or it doesn't terminate, and we keep picking points that are outside the union of the balls thus far found, right? And that would, okay, then what would that be? He says that the points constructed in this way satisfy the following. Have what? They have the distance between yk and yj, yeah, would you say greater than epsilon? Greater than or equal to epsilon for 1 less than or equal to j less than k. If the procedure for selecting y sub j's does not terminate, then the sequence y sub j has no convergent subsequences.
Yeah, that makes sense.
He says it follows that the choice of yn plus 1 is impossible, so that x is covered by n balls of radius epsilon with centers at y1 through yn. In particular, x is totally bounded, and 5.2 implies 5.3. Jonathan sees it. I don't know if everybody else does.
Well, we know that convergent implies Cauchy, correct?
Convergent implies Cauchy, right?
So if I take a subsequence of that sequence and I say this is convergent, that would mean that that subsequence also has to be Cauchy.
Right.
But that's impossible because all of the terms are greater than epsilon apart from one another with respect to that measure.
Aha. Right. So what's special about the n here? I think I think that's the thing that.
I don't know why I don't get the n.
He says, having chosen y1 through yn, let yn plus 1 be any point in the complement, provided the union doesn't coincide with x, otherwise we stop. I think his point is that that it can't go on forever. It has to stop.
Yeah.
If it goes on forever, that's where we get the contradiction that you just pointed out. Because if it goes on forever, then that means we have a, as he says here, a sequence with no convergent subsequence. Right? But what did 5.2 say?
Every sequence has a conversion.
Right, every sequence has a convergent subsequence, right? So if this went on and on forever, then this would be a sequence without a convergent subsequence, which is no allowed. So it must not go on forever. It must terminate at n. Terminating at n shows it's totally bounded, because we have a finite number of balls of fixed radius epsilon, which cover the thing. But this is also, argument works for any epsilon greater than 0, which shows you totally bounded. My head. All right, I'm gonna go on. And the next few things I'm not going to prove, but I will write them down at least. All right. So lemma 5.2: a totally bounded metric space is bounded. All right. What is it? What's the difference between totally bounded and bounded? What do we mean by a metric space being bounded? Again, all of this for metric spaces. So I'm talking about a totally bounded metric space. Can you guys tell me what was the definition of what did bounded mean? I'll tell you. This means that the distance, right, from x to y is less than what? What's that? Less than some fixed constant for all x and y, right? This is bounded. Given my pictures, this isn't terribly surprising, right? It kind of makes sense. If you can cover the whole thing with a finite number of balls of a particular radius, surely that means that two given points can't be that far apart. Seems reasonable. That is not a proof. All right, lemma 5.3. Any subspace of a totally bounded metric space is totally bounded. Any subspace of bounded X is tot bounded. All right. Lemma 5.4. A subset E of Rn, all right, is totally bounded if and only if E is bounded. Ooh. What does it mean for a subset of Rn to be bounded? It's what? It's contained in some open ball, right? So E bounded means there exists beta positive such that what? Such that for any, let's say X in E, we have, well, let's say X and Y in E, right? Well, no, that's still not it. I'm not, I mean, there's an existence. Oh, sorry. Such that yeah, there exists and x naught in E, right? Such that the ball centered at x naught of radius beta contains E. Right, so like a unit cube, for example, in R3 is bounded because I can blow a bubble around it, right? I can make a big ball centered at the center of the cube and it contains it, right? It's bounded. We can enclose it with a ball of finite radius. Yeah. Well, there is a characteristic sort of diameter for a subset of Rn, and I could use that like the B, right? Like, I think if you pick any pair of points in the unit in the cube, like the unit cube, they're going to be no more. I mean, depending which unit cube we're talking about. If we're talking about the 0 to 1, 1, then I don't. What's a good diameter there? What? 2 will work, but yeah. Double, yeah, right. So 2 beta would serve as the B. Fair enough, these are slightly different ideas, but when I teach Calculus 3, when I talk about bounded, I'm talking about that, like there exists a ball that encloses it. But, I mean, this, you're right, Sam, this is a different, quite, like a slightly different idea. Yeah.
I guess I'm just trying to understand that by conditional integrated state for Rn, the penalty row would be false for arbitrary limit spaces. Like it seems like that applies to thing about it applies to really bounded.
Well, totally bounded implies bounded. So if totally bounded implies bounded, then theorem 5.1 says that x is compact implies x is bounded and complete. So I don't think it is I think you're right. I don't think it is limited to Rn, but the emphasis here is for Rn. You just talk, because when you're talking about Rn in a real analysis course, you might not be talking about the concept of totally bounded. You might just talk about the concept of bounded. That's, I think, the intent of this part of the section is just to roll around in the real analysis here for a minute. Don't worry, we'll get it off us eventually. So that's the wrong mental picture. What's that?
I mean, in the discrete space, the discrete space is bounded but not totally bounded. Well, if I understand the question correctly, then there are many spaces that bounded is not like totally bounded.
Well, yeah, I must be missing something.
It's obvious that totally bounded is really quite different than bounded, right?
I guess I'm just confused because it seems like bounded, you said, means that there's a single ball that contains the whole thing. So how does that not apply to
They're
a single ball is defined as a circle?
there are 2 different definitions of bounded on the board right now.
Oh, sorry.
So what was the resolution?
I was just misreading the definition of totally bounded.
Oh, okay. Yeah, it has to be for each epsilon greater than 0. There's a, yeah. Okay, anyway, getting to the point here. He says, okay, so a subspace of Rn is complete if and only if it's closed. All right? And theorems by theorems 2.3 and 2.4 from last time, he says, consequently, a subspace of Rn is totally bounded and complete if and only if it's closed and bounded. All right, so theorem 5.1 specialized to Rn becomes the Heine-Borel theorem. Theorem 5.5. It says the following are equivalent for E, a subspace, a subset of Rn, 5.1 prime, E compact, 5.2 prime, every sequence has convergent subsequence, and 5.3 prime, E is closed and bounded. What I was trying to say, and I think you guys have already figured out what it is that I wasn't saying or whatever, but this concept of bounded and this concept of bounded are interchangeable. Like if I have, for a subset E, that the distance between any 2 points in E is less than a fixed distance, then I can show that there exists a point somewhere in there such that there's a ball big enough around that point that contains the whole set, and vice versa. If I have a ball like this, then I can also argue that there exists a fixed distance which bounds the distance between any 2 points. You said 2 beta, right? Would be at least, maybe not the smallest choice, but certainly a choice that works, right? Depending on the details of the set, but who cares? Anyway, so there you go, that's the Heine-Borel theorem. So what's left to prove in theorem 5.1? What's that? 5.3 implies 5.1? Yeah, that would be one path. Not the path he takes in the book, though. So his theorem 5.6 shows 5.3 implies 5.2. All right. So we're going to look at that, theorem 5.6 here. And I was kind of excited about this theorem for the purposes of this class because it shows an example of what's called a diagonalization argument. All right, and this technique of proof is something maybe you haven't seen before. So this maybe will open your eyes to another method of proving things that yes, it's the diagonalization in Cantor's theorem. Yeah, I think it's that same trick. So here we go. This is theorem 5.6. Which is really a subpart of theorem 5.1. Here's the statement: let X be a totally bounded metric space all right, then every sequence in X has a Cauchy subsequence. Well, that's not exactly 5.2. 5.3 implies 5.2, is it? But you can see how they're related. See, think about this. If we assume 5.3, that X is totally bounded and complete, right? And if we can show that every sequence, if we can show that every sequence has a Cauchy subsequence, then since it's complete, Cauchy implies convergent, which gives us 5.2.